Welcome to our YouTube channel on Mastering Simple Harmonic Motion. In this video, we delve deep into the world of oscillatory motion and explore the fundamental formulas that govern simple harmonic motion. Whether you are a student learning about simple harmonic motion for the first time or simply someone looking to refresh your knowledge, this video will guide you through the essential formulas step by step. By the end, you will have a solid understanding of displacement, velocity, acceleration, and energy, and more in the context of simple harmonic motion. Let's dive in. In this case, I'm going to provide us with 20 different formulas which govern simple harmonic motion. Starting with the first one, which is displacement equation. In displacement equation in simple harmonic motion, this is being denoted by x, which is equals to a cos into bracket of omega t plus first constant. This equation represents the displacement which is denoted by x of an object undergoing simple harmonic motion, and our a here is the amplitude, and we have omega, which is the angular frequency, and the symbol this symbol here is our initial phase constant, and the t we have here is the time period. Next thing we have on the list is velocity equation. In simple harmonic motion, the velocity equation is being denoted by v, which is simply going to be minus a omega sine into bracket of omega t plus first constant. It gives the velocity, which is being denoted by v, of the object at any given time during simple harmonic motion. The negative sign indicates that velocity is in the opposite direction to the displacement. What about equation for acceleration or acceleration equation? This is being denoted by a, which is going to be negative a omega square cos omega t plus first constant. This equation provides the acceleration, which is a of an object at any given time. It is proportional to the displacement, but in the opposite direction. That is why we have negative a. Next thing we have on the list is angular frequency. Angular frequency is being denoted by omega. This is simply going to be 2 pi, the frequency itself. So in this case, we can say angular frequency is the rate of change of phase of the oscillation with respect to time. It is related to the frequency of oscillation. Next thing we have on the list is frequency. In this case, frequency is being denoted by f or this symbol. We can say frequency is the same thing as 1 divided by your time period. In simple time, you can say frequency is the numbers of oscillation per unit time, while the capital letter T here, down here, is simply the period, which is what? The time taken. So, next thing we have on the list, we have time or period, which is what? T. In this case, the period is denoted by 2 pi divided by omega. And I need you to understand that omega is the same thing as the square root of what? M divided by k. Alright. In this case, we can say the period t is the time taken for one complete oscillation. It is inversely proportional to the angular frequency. Next thing we have the first constant. This is a symbol for first constant. When we talk about the first constant actually determines the initial position and velocity of the oscillating object at t, which is equals to what? At t is equals to 0. Next thing we have on the list, we have total mechanical energy. In total mechanical energy is being denoted by E, which is a half spring constant which relies on amplitude square, which is what E is equal to half Ka square. In this case, we can say this equation represents the total mechanical energy of the oscillating system, where K is the spring constant and A is the amplitude of oscillation. Next thing we have on the list, we have the kinetic energy. Kinetic energy is being donated by Ke, which is known as a half mv square. In this case, kinetic energy is the energy associated with the motion of oscillating object. It depends on the velocity of the object. Next thing we have on the list is the potential energy, sometimes being denoted by U or PE. This is simply going to be half our spring constant relies on distance to the power of 2. Potential energy U is the energy stored in the restoring force of oscillating system. It depends on the displacement, which is x, from the equilibrium position. Next thing we have on the list is maximum velocity, which is being denoted by Vmax. In this case, maximum velocity is the same thing as saying O is equal to A multiplied by omega. Or our amplitude is going to multiply by the square root of what? M divided by K. This formula gives the maximum velocity reached by the object during simple harmonic motion, where our A is the amplitude and omega is the angular frequency. Next thing we have on the list is the maximum acceleration. Maximum acceleration is being denoted with small letter m, then max, which is equal to A multiplied by omega square, which is the same thing as saying A into bracket of square root of what? M divided by K to the power of 2. It represents the maximum acceleration experienced by object during simple harmonic motion. In this case, the A is the amplitude, while omega is the what? Is the angular frequency. Next thing we have on the list is the time period of a pendulum. The time period of a pendulum is being denoted by T, which is equal to 2 pi into square root of L divided by G. In this case, this formula gives the period of a simple pendulum, where L is the length of the pendulum, G is the acceleration due to gravity. And next thing we have on the list, we have the time period of a mass spring system. In this case, this is going to be T, which is 2 pi into the square root of what? M divided by K, which is the same thing as saying T is going to be 2 pi omega. This represents the period time of the mass spring system undergoing simple harmonic motion, where M is the mass and K is the spring constant. Next thing we have on the list is frequency of a mass spring system. In this case, the frequency of a mass spring system is being denoted by frequency, which is 1 divided by 2 pi, multiplied by the square root of K divided by M. This formula gives the frequency of mass spring system undergoing simple harmonic motion, where K is the spring constant and M is the mass. Next thing we have the first differences between displacement and velocity. In this case, we're going to have our first constant, which is going to be tan inverse of negative omega x naught divided by v naught. It calculates the first differences between displacement and velocity at time, which is equal to 0. In this case, we can call our x naught to be our initial, and v naught will also be our initial velocity. Next thing we have on the list, we have the displacement at any time. Displacement at any time is being denoted by xt, which is simply going to be a cos omega t plus phase constant. This simply represents the displacement x of an object at any given time during simple harmonic motion. In this case, our A is the amplitude, omega is the angular frequency, and this symbol is simply the phase constant. Next thing we have on the list is velocity at any time. Velocity at any time is being denoted by V, small letter t, which is simply going to be negative A omega sine into bracket of omega t plus phase constant. This formula gives the velocity v of the object at any given time during simple harmonic motion, where A is the amplitude, omega is the angular frequency, and I'm sure you are already familiar with the phase constant. The last but not the least, we have the acceleration at any time. Acceleration at any time also, just like the previous one, is simply going to be denoted by A into bracket of t, which is going to be negative A omega square cos into bracket of omega t plus the phase constant. It represents the acceleration A of the object at any given time during simple harmonic motion, where A is the amplitude, omega is the angular frequency, and the last thing we have is the phase constant. Next thing we have is the relation between period and frequency. The relation between period and frequency is simply going to be t multiplied by f, which is simply going to be 1. This formula shows the inverse relationship between the frequency and the period of oscillation. Their product is always going to be 1, which is the same thing as saying t multiplied by frequency is also going to be 1. So this is it for this problem. Thank you for watching. Feel free to check on my YouTube account. I also have some basic problems and solution under the simple harmonic motion. Don't forget to share, like, and subscribe. Thank you very much. See you next time.